Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to cover topics from your online Math 136 class at Ivy Tech for week 13. So we're going to start with new material from chapter 6. There are only two sections this week, 6.7 and 6.8, and then I'm going to review some of the other stuff from chapter 6 just kind of briefly at the end, just since you have your chapter 6 quiz due this week as well. So let's start with 6.7, which is all about financial models. So the first objective that we're going to cover is actually being able to determine the future value of a lump sum of money. So we have a couple of formulas in this section that we're going to have to deal with. The first one is one that you might have seen before. It's a simple interest formula. So if some principal P is borrowed for a period of T years at an annual interest rate of R, then in order to find the actual interest, all we have to do is multiply those three things. We take principal times rate times time. Now it's important to note that the rate is an annual rate and that the time is in years. So if you're given time in months, you need to divide by 12 in order to get it into years. So this is the interest charged and it's called simple interest. Now, the other type of interest that we have is compound interest, okay? So the amount A after T years due to a principal P invested at a rate R, so all of that's the same, compounded N times per year is given by this right here. So A is going to be the future value, and that's going to be equal to the principal times 1 plus the rate divided by N, which is the number of times that it's compounded in a year, raised to the power N times T. So we're going to do some examples with this. But first I want to talk about what different values of N might be in different situations that you're going to see. So if you have something that's compounded annually, that means that every year your balance is reconfigured and that the interest that you've earned that year is included in your new balance for the next year. So that just happens once per year if it's annually. So N is going to equal 1 in that case. So if we go back to our formula, if we have annually, N is just going to equal 1. So we're going to have a 1 here, and we're going to have a 1 in our exponent as well. Now, if you have semi-annually, that means that it's twice per year. So N is going to equal 2. Quarterly is 4 times per year, so N is going to equal 4. Monthly is going to be 12 times a year, so N is equal to 12. And daily is going to be 365 times per year, so N equals 365. So if you're investing money, you'd like to have that money compounded as frequently as possible, because really what's happening is after each one of these periods, so for example, if you have quarterly, every 3 months your balance is going to be reconfigured, and any interest that you earned in that quarter is added to your original balance, and then you earn interest on all of that money. So it's compounded so that you continue to earn interest on your interest. So let's take a look at these examples here. I would make sure you get a calculator out, okay? So we're going to go through the situation where we're investing $1,000 at an annual rate of 10%. And we're going to do compounded annually, semi-annually, quarterly, monthly, and daily. And we're going to figure out how much that would yield after just 1 year. So time is going to equal 1, which makes this a little easier to do, okay? So if you have annually compounded, that means N equals 1. So we're going to use our formula. We have A equals P times 1 plus our rate, and then the rate should be divided by N, okay? But R divided by 1 is still just going to be R, so we just leave that there. And then the power is going to be the 1 times 1 power, because we have 1 year and N equals 1. So this, they didn't write anything here because 1 times 1 still just gives you 1. We don't need to raise it to the first power because that's not actually going to do anything. So in your calculator, what you're going to type is 1,000, and then you're going to put a parenthesis, and then you're going to do 1 plus 0.1. So you need to make sure that you change percentages into decimals. So 10%, if we move our decimal 2 places to the left, we get 0.10. So if you do this in your calculator is going to do the addition for you and then multiply. You should get $1,100. Now, this next one, for semi-annually compounded, that means that it happens twice a year. So what you're going to do is you're going to take your principal, which is 1,000, and then you're going to do 1 plus your rate divided by 2. So you take your 10% and you divide it by 2, and you get 0.05. And then you just square it because you have to the n times t power, so you have the 2 times 1 power here. Now in your calculator, I would actually recommend, instead of putting 0.05 in, to actually put 0.10 divided by 2. So have your calculator do the work for you, especially when you get down here and the numbers are not so nice. So what your calculator will do, you have to make sure you put the parentheses in, but it's going to add these first and then square it and then multiply by 1,000. And you should get a little bit more money after that first year, $1,102.50. So I want you guys to go ahead and try n equals 4, n equals 12, and n equals 65 in your calculator, and make sure that you're able to get these to work. I'll give you guys maybe a minute to try those. Okay, so hopefully you were able to get those to work. If you got a couple of them to work, then it means that you know what you're doing in terms of putting it in your calculator. But one thing that I kind of want to stress, just so that you don't get any rounding errors on my math lab, is that instead of doing it the way that they have it here, I would actually, in your calculator, type in, like for this last one, for example, I type 1,000 and then I do a parenthesis and then I do 1 plus 0.1 divided by 365, and then I'd end my parenthesis and raise it to the 365th power, instead of going ahead and doing the 0.10 divided by 365 to get this decimal, just because you might end up with some kind of rounding error. Now, one thing to keep in mind is these all looked pretty nice because we had 1 year. So if you have 2 years, for example, all of your exponents are going to need to be multiplied by 2. So for example, the exponent here is just 1, so we'd have to do 1 times 2 to give us the second power. Here we'd have 2 times 2, which would give us the fourth power, 8th power, 24th power, and so on. So you need to make sure that you keep in mind that this one was kind of simple because we had 1 year, and that you always have to raise your exponent or raise this part right here, this 1 plus r over n, to the n times t power. And you need to make sure that if you put the power in and it has multiplication in it, so for example, if you had the 2 times 2 power, that you either put this to the fourth power, or when you raise it to the power, you put parentheses around your exponent. Okay, we have one other type of compounding, which is continuous compounding. So the amount A after t years due at principal P, all same stuff, at an annual interest rate of R is going to be compounded continuously. Then we have this formula here, where the amount is equal to the principal times e to the R times t power. So let's take a look at an example of actually using this. So we're going to use this formula down here. So let's say that we want to find the amount A that results from investing 2,000 bucks at an annual rate of 8%, and it's compounded continuously for just 1 year. So what we're going to do is we're going to plug everything in. Okay, so we have our 2,000, which is our principal, times e to the 0.08 times 1 power. Okay, 0.08 is our rate, 1 is our time. And you just need to plug this into your calculator. Okay, I'm not sure why this was written again. This is the same as this. But if you plug this into your calculator, you need to use your E button. Okay, and then you're going to raise it to the power of 0.08 and multiply by 2,000. You should get $2,166.57. Okay, so hopefully you were able to get that. One other thing I wanted to point out is with the interest kinds of questions, make sure your answers always make sense, particularly on quizzes when you don't have more than one attempt or exams. Your answer should be kind of in the same ballpark. So if we're just talking about 1 year of time, you shouldn't earn that much interest. So if you ended up with $20,000, something would definitely be suspect there. And you also shouldn't end up with less money than what you started with since you're earning interest. And then the same thing is true with these types of questions back here. For each one, we earn a little bit more every time because it's compounded more frequently, but it's not drastic, okay? So if we looked at this over the course of many years, it would change, but we're only talking about 1 year here, so we're not earning very much interest. All right, let me get back to that. Okay, now the second objective in this section is to actually be able to calculate something called the effective rates of return. So let's look at an example here. Let's suppose that you have $1,000 in a bank account and a bank offers to pay you 3% annual interest, and it's going to be compounded monthly. So what happens is that in 1 year, you're going to have this much in your account. So you're going to take your $1,000 times 1 plus your 0.03, which is your interest rate. You're going to divide it by 12 since it's compounded monthly, and then you're going to raise that to the 12th power. And if you do that in your calculator very carefully, you get $1,030.42. So the interest that we actually earned is $30.42. So if we use the formula I equals PRT, where our time is just 1 year, the interest that we earned is $30.42, and then the principal is $1,000. If you actually go ahead and solve that, you're going to get a simple interest rate of 0.03042 or 3.042%. And that interest rate is actually known as the effective rate of interest. And what it is, it's just the equivalent amount of a simple interest rate that would yield the same amount as compounding after 1 year. So for example, when we have 3% interest compounded monthly, that would be the same thing as simple interest at 3.042%. Now, there are formulas here that we can use to calculate the effective rate of interest, R sub E, of an investment. And all we have to do is take 1 plus our rate divided by n raised to the nth power, and then subtract 1 from it. Or if you have continuous compounding, then you take e to the r power and subtract 1. So let's compare a couple of different bank offers. Okay, so let's suppose that you want to open a money market account. And this is when it's most useful, is when you're trying to compare different offers to see which one is actually better, because it's hard to tell based on just the interest rate because we have different types of compounding. So let's say that you visit 3 different banks, and Bank A offers you 4% annual interest compounded daily. Bank B offers you a little bit higher of an interest rate, but it's only compounded monthly. And then Bank C offers you compounded continuously, but it's an even lower rate. So if we want to find the effective rate, all we have to do for Bank A, since it's compounded daily, is take 1 plus our rate, which is 0.04, divided by n, which is 365 because it's compounded daily, and then raise it to the 365th power. And then once we have all of that, we subtract 1 from it. And if you do that very carefully in your calculator, again, you get 0.0408084. So you're noticing that it's pretty close to the 4%, but it's a little higher because this is compounded daily. So this is actually an effective rate of interest of 4.081%. So our 4% compounded daily is equivalent to 4.081% of simple interest. Now for Bank B, we're going to do the same kind of thing, except it's compounded monthly. So we have n equals 12, and then our interest rate's a little higher, 0.041. And if we do this in our calculator, you should get 0.0417793, which would be 4.178%. Okay, so Bank B is a little bit better than Bank A. So 4.1% compounded monthly corresponds with 4.178% of simple interest. Now Bank C is continuously, so we have our formula where we raise e to the power of our rate and then subtract 1. So this is probably the easiest formula. So we do e to the 0.0395 power and then we subtract 1, and you should get 0.0402905, which is 4.029%. So 3.95% compounded continuously is equivalent to 4.029%. So Bank B is definitely your best option in this scenario. Okay, and now let's look at determining the present value of a lump sum of money. So we have a couple of present value formulas. You can also use the other formulas that we looked at, and you would just be solving for a different variable, but these work as well. So the present value P of $8 to be received after T years, assuming interest rate of R, compounded N times a year, so all the same kind of jargon there, is going to be given by this. So if we're trying to figure out how much do I invest now in order to have this future value, we're going to use this formula here, where we take A times 1 plus R over N, and then we raise it to the negative NT power. So it's very similar to the last one, except the A and the P are flip-flopped, and our power is now negative. And then if we're trying to find compounded continuously, this one also looks the same. A and P are flip-flopped, but then our power is going to be negative. So let's take a look at an example here. So a zero coupon or non-interest bearing bond can be redeemed in 10 years for $1,000. How much should you be willing to pay for it now if you want a return of 7%, and then a return, compounded monthly, and then a return of 6% compounded continuously? So we're trying to solve for P. We're trying to figure out what is it worth presently so that it should be worth $1,000. So we take our $1,000, that's our future value, multiply by 1 plus the 0.07, which is our rate, divided by 12, since we have compounded monthly, and then our power is going to be the negative 12 times 10th power, because it's the 10th power because we have 10 years. Now this is one, when you put this into your calculator, I would definitely try this because this is a little different. You need to make sure that when you put in the exponent, you hit your caret key for your exponent, and then you put a parenthesis, and then you do negative 12 times 10, and then you end your parenthesis. And if you do this very carefully, you should get $497.60. So that means that you should be willing to pay $497.60 today if in 10 years it can be redeemed for $1,000 if you want to be earning 7% interest compounded monthly. Now, if you want 6% compounded continuously, then we use our continuous compounding formula. So we say that our principal is equal to our $1,000, that's our future value, times e to the power of negative 0.06 times 10. So it's our rate times our time, but it's negative. And again, when you do your exponent, you need to make sure that you put the exponent in parentheses. And you should get $548.81. So that means that if you're interested in getting 6% interest compounded continuously, you should be willing to pay about $548.81 today for that bond. Okay, now let's look at determining the rate of interest or the time that it's required in order to maybe double a lump sum of money. So this is a fairly typical question. So we want to know what annual rate of interest compounded quarterly should you seek if you want to be able to double your investment in about 6 years. So we're going to have our formula down here. This is our compound interest formula. And we're going to plug in what we know. Okay, so our principal, it doesn't matter what it is. It could be $100 or $1 million. But our future value, we want it to be twice what the value of the principal was. So for example, if our principal was $100, we want A to be $200. If our principal was $1 million, we want A to be $2 million. So it just needs to be twice whatever the principal is. So we can set it up as 2P for our future value is equal to our P, our principal, times 1 plus rate, which is what we're not sure of, divided by 4, since we have compounded quarterly, and then our power is going to be the 4 times 6 power, because we have quarterly times our 6 years. So it's the number of times that it's compounded total, which would be 24. Now, if we simplify this a little bit, if we divide both sides by p, we're just going to get rid of it, and we're going to get 2 equals 1 plus r over 1 plus r over 4 to the 24th power. And then since we have this 24th power, this is not particularly nice, but we can actually use our calculator to take the 24th root of both sides. So you're going to do the 24th root of 2, or if you do not have the ability to put in different roots in your calculator, you can do 2 to the 1 over 24th power. That would be equivalent. So again, 2 to the 1 over 24th power. And that's going to be equal to 1 plus r over 4. And then we just solve this by subtracting 1 and then multiplying by 4 to get r by itself. So r would be equal to 4 times the 24th root of 2 minus 1, which if you put this into your calculator very carefully, you get 0.117289 and so on, which means that we would need an annual interest rate of 11.72% in order to be able to double our principal in about 6 years, if we're getting compounded quarterly. So again, if you don't have the ability to do the 24th root of 2, you can do 2 to the power 1 over 24, and that will work just fine. Okay, let's look at this. So let's figure out how long it's going to take to triple at this rate. So, oh, sorry, we have a compounded continuously question. We're going to do doubling and then tripling for the compounded continuously. So compounded continuously, we have our formula down here. Again, if we put in 100 bucks, we want 200 bucks. 1 million, we want 2 million. So we're just setting A equal to 2 times P. And then we're going to divide both sides by P. So we get 2 equals E to the 0.06T. And then hopefully this looks familiar when we solved our equations from last time, I believe. We take natural log of both sides. So we have natural log of 2 equals natural log of E to the 0.06T power. Natural log is going to allow you to bring your exponent out front as a factor, and then ln of E is going to go away because that's just 1. So we have ln of 2, that's just going to be some number. It's not a very nice number, but it's a number. 0.06T we bring out front because exponents we're allowed to bring out front when we have a logarithm or a natural log. And ln of E is just 1, so we can just ignore it. And then we divide both sides by 0.06, so we get T equals ln of 2 over 0.06, which is 11.55 years. And if we want it to triple, we just substitute 3p in instead. So it's going to be the same process. We divide both sides by p, we take the natural log, we move our exponent out front, and since we have ln of E, that just goes away because that's just 1. And then divide by 0.06. So it's just ln of 3 divided by 0.06, which is going to take a little longer, about 18.31 years, in order for it to triple. Okay, now let's take a look at section 6.h, which goes through exponential growth and decay models, and then also logistic growth. So if you have something with uninhibited growth, it's going to follow this formula here, where you have A of t equals A naught times e to the kt power. So you have something where you're starting at some initial amount, and then it's growing exponentially here. And then if you have decay, you're going to also start at A naught, but this one is going to be decaying, okay? So if we take a look at uninhibited growth of cells, that's a fairly typical kind of example. N is going to be the number of cells in a culture after time t has passed. And so we have this formula here where N of t is the number of cells in a culture after time t, equals N naught, which is the initial number of cells. So for example, if we start with 1,000 cells, it would be 1,000. And then we have e to the kt power. K is going to be a positive constant that represents the growth rate, and T is going to be the amount of time. And this is going to be growth since K is greater than 0. Since we have a positive rate, that means that it's actually getting larger. So let's take a look at this example here. A colony of bacteria grows according to the law of uninhibited growth, according to the function n of t equals 90 times e to the 0.05 t power, where n is measured in grams and t is measured in days. Okay, so you have to pay attention to the context of the question because they tell you what measure of time you should actually be using. And for part A, we want to just determine the initial amount of bacteria. So if you take a look, it looks like whatever's in spot N0 in front of this E, that's going to be our initial amount. So it looks like 90 is our initial amount that we're starting with. The other thing that you could do to figure this out is you could plug 0 in for T, because initial amount is going to be the amount after time equals 0. So if we plug time equals 0 in, we're going to get 90 times e to the 0 power, which is just going to be 90 times 1, or just 90 cells. Now the growth rate of the bacteria, we just look at our exponent here, 0.05, that corresponds with 5%, so that's going to be our growth rate. Now if we want to know what the population is after 5 days, that means that we plug 5 in for T, And if we plug that in, we have 90 to the e times 0.05 times 5 power. Make sure when you put this in your calculator, I'm going to give you a minute to do that to make sure you get the answer. Make sure you put that exponent in parentheses. Okay, so hopefully you got 116 cells there. You should do 90 and then hit your E button and then hit your caret and then do a parenthesis 0.05 times 5. And then for this one, it's asking how long is it going to take for the population to reach 140 cells. So instead of giving us time, they give us the amount of cells that we want. So we plug 140 in for n of t. So we say 140 equals 90 times e to the 0.05 t power. And we want to get e by itself, and then we're going to use natural log. So we divide. So we have 140 divided by 90 equals e to the 0.05 t power. And then we take natural log of both sides. You'll notice they took 140 over 90, and they simplified it to 14 over 9. And then we go ahead and divide by 0.05 to get t by itself. And we have ln of 14 over 9 divided by 0.05, which should give you about 8.8 days. And then if we want to know what the doubling time is, that means that from 90 we want to have 180 because that would be doubling. And if we divide both sides by 90, just like we did down here, we get 180 over 90, which is just going to be 2. So we get 2 equals e to the 0.05 t power. We take natural log of both sides. So we have ln of 2 equals 0.05 t, and then we divide both sides by 0.05, and we're left with 13.9 days. So it takes a little bit longer in order for us to have it double rather than reach 140, which makes sense because doubling is going to be more cells. Now you could always plug this in to make sure that this works, and I would highly recommend that on quizzes and exams that you do this. So for example, you would pretend that you have 13.9 days and you'd plug that into your equation on the right-hand side and make sure that you end up with 180 over here. So if you do 90 times e to the 0.05 times 13.9 power, you should get something around 180, which will tell you that you did this calculation correctly. Now, the main reason that I would recommend doing this is because the process that we just went through is much, much trickier than the process that we went through for part C, where we're given time. So if you pretend like you know time, and then you plug it in, that will let you know if you did it correctly. All right, let's look at this example here. So a colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the time in hours, express n as a function of t. So we know that we're going to have n of t equals n naught times e to the kt power because that's the general form of our equation. And then for part B, it tells us that the number of bacteria doubles in 2 hours. So we want to actually find the function. So we know that whatever initial amount we put in, this n0, after 2 hours, so after time equals 2, we're going to have twice as much as what we started with. So we're going to, for example, if we had 100 here, we're going to have 200 cells. So we set this equal to 2 n naught. And then we divide both sides by n naught. So we have 2 equals e to the 2k. And now that we have e by itself, we can take natural log of both sides. So we have ln of 2 equals 2k, and then we divide by 2. So we get our growth rate of k equals ln of 2 over 2, which is approximately equal to 0.3465736. So our function would be n of t equals n naught, which is our initial amount, times e to this power times time. So if we want to know how long it's going to take for the colony to triple, we just say 3 times n naught equals n naught. So our new amount is 3 times our original amount. And then instead of the letter k, we actually know what k is from solving part B. And we divide by n naught, and then we take natural log, and then we divide one more time to get t equals ln of 3 over 0.3465736, which gives us about 3.2 hours. Now again, I would take this 3.2, plug it back into your original equation, and make sure using some value like 100 here, make sure that you end up with 300, which would be tripling. And then how long will it take for the population to double a second time? So if the population doubles in 2 hours, it's going to double a second time in 2 more hours, which would be about 4 hours. Okay, and then let's look at this equation where we have uninhibited radioactive decay. So solving this is going to be very, very similar, okay? But the only main difference is that we're using A because we're talking about amounts, not necessarily numbers, because a lot of times with decay, we're going to be talking about radioactive material. And then instead of having a growth rate that's positive, we're going to have a decay rate, so that's going to be negative. Now, A sub 0 is going to be the original amount, and K is going to be a negative number that represents the rate of decay. So let's take a look here. Let's say we have traces of burned wood along with ancient stone tools found in an archaeological dig in Chile, and they were found to contain approximately 1.67% of the original amount of carbon-14. And we know that the half-life of carbon-14 is about 5,600 years. So what we're trying to figure out is approximately when the tree was actually cut and burned. So we're going to use our equation for decay right here. Now, we know that whatever our original amount is, we now have half of that after a time of 5,600 years. So we know that at 5,600 years, our original amount has been cut in half. So that's what we're doing right here. And then we're dividing both sides by A naught. So we get 1/2 equals e to the 5,600 times k power. Now this is useful because we're trying to solve for k. We need to actually know what the decay rate actually is. So now if we take natural log of both sides and then divide by 5,600, you're going to have natural log of 1/2 divided by 5,600, which should give you a negative number because we're talking about a decay. So it's negative 0.000124. So that's our value for k. And what we're actually going to do now is we're going to substitute this in for k. We have the k times t power, that's this part right here. We still have our e, we still have our initial amount. And we're not sure what the initial amount is, but we know that currently we have 1.67% of the initial amount. So we take 1.67% of our initial amount by multiplying, and we divide both sides by A naught, and we get 0.0167 equals e to this power. We take natural log of both sides and we divide. And we should get 33,003 years. So we have ln of 0.0167, which is the percent of the original that we thought we had. And then we divide it by our decay rate. Okay, now we're going to talk about logistic models. Okay, so in a logistic model, the population P after a time t is given by this function here. So P of t equals C divided by 1 plus A to the A times E to the negative BT power. A, B, and C are going to be constants. A is greater than 0 and C is greater than 0. And then the model is a growth model if B is greater than 0, and the model is a decay model if B is less than 0. So let's take a look at kind of a depiction here. So we have our initial amount, P of 0. We have an asymptote here at y equals c, and we have an inflection point that happens at 1/2 c. And then the same is true with decay, okay? But our starting point is going to be higher, and then our inflection point will be lower, and it's going to approach this value here. So let's look at some of the properties here. So the domain is going to be the set of all real numbers. The range is going to be the interval from 0 to c, where c is called the carrying capacity. Okay, so it's the maximum amount. There aren't going to be any x-intercepts, but the y-intercept is going to happen at p of 0. There are going to be two horizontal asymptotes that we can see. If we go back, we have y equals 0 as one of the horizontal asymptotes, and then y equals c is the other. It's going to be increasing if b is greater than 0 and decreasing if b is less than 0. There's going to be an inflection point where p of t equals 1/2 of the carrying capacity. And then the inflection point is the point on the graph where the graph changes from being concave up to concave down or the other way around. And then the graph is smooth and continuous. It doesn't have any corners or gaps. So let's take a look at this example here. So we have this wood product model. It's classified, it classifies wood products according to their lifespan. And then there are 4 different classifications. There's short, which is 1 year, medium short, which is 4 years, medium long, which is 16 years, and then long, which is 50 years. And then based on the data that's obtained by the European Forest Institute, the percentage of remaining wood products after T years for wood products with long lifespans, like those that you would use in the building industry so that they last a long time, is given by this formula here, where we have P of T equals 100.3952 divided by 1 plus 0.0316 e to the 0.0581 t power. Okay, so this is our logistic model. Now the decay rate is just going to be given by this right here. So we have the absolute value of negative 0.581, which is just 5.81%. So we have a decay rate of 5.81%. And then we want to know what is the percentage of remaining wood products after 10 years. So what we actually do is we just plug 10 in for T. So we have 100.3952 divided by, and then make sure in your calculator you put a parenthesis for your denominator. And then you have 1 plus 0.0316 e to the 0.0581 times 10th power. Make sure you close your parenthesis. Make sure when you do your exponent that you put your exponent in parentheses here. So we're finding P of 10 and we get 95. So that means that 95% actually remains after 10 years. Okay, now let's answer how long does it take for the percentage of remaining wood products to reach 50%. So what we're actually going to do is we're going to plug 50 in to the left-hand side because now we know what percentage remains. It's going to be 50%. And then we have 50 equals 100.3952 divided by 1 plus 0.0316 e to the 0.0581 t power. So in order to solve this, we go ahead and multiply both sides by this denominator. And then we have divided by 50. And then we subtract 1, divide by the 0.0316, and now we can take natural log, move our exponent out front, and divide. So we have ln of 31.8956 divided by the 0.0581, which gives us 59.6 years. And then question D asks you to explain why the numerator in the given model is reasonable. Now the numerator is 100.3952. The maximum percentage of wood products remaining is going to be 100%. So that means that this 100.3952 is a fairly reasonable number. And if you had time equals 0, this whole denominator would just become 1. So we'd have 100.3952 over 1, which would just be about 100%. Okay, now what I want to do for the last few minutes is go ahead and review some of the previous material from Chapter 6, since you do have a Chapter 6 quiz this week. So let's go way back. I don't remember exactly which section this is, but let's go back to finding an inverse function. So let's say that we're given the function f of x equals 2x plus 1 over x minus 1. X cannot equal 1 because that would make our denominator 0. We know this is 1 to 1 and we want to go ahead and find the inverse. So hopefully you recall, in order to find the inverse, all you have to do is just interchange x and y and then solve for y. So in this case, we take our y, which was our f of x, and we put an x in its place, and we take our x's and we put y's in their place. So we have x equals 2y plus 1 over y minus 1. And then we multiply both sides by the denominator because we're trying to get y by itself, so we have to get rid of this denominator here. So we have x times y minus 1 equals 2y plus 1. And then we go ahead and distribute, so we have xy minus x equals 2y plus 1. And then you want to get everything that has a y on one side and everything else on the other side. So I'm going to take this 2y and subtract it so that it's on the left-hand side with this piece right here. And then I'm also going to add x so that it's on the other side. So we're getting everything that has a y on the left-hand side and everything else on the right-hand side. So we have xy minus 2y equals x plus 1. And then we factor out a y. and then we divide. So we get y equals x plus 1 over x minus 2. And we like to write this instead of y equals, we write it as f inverse of x equals x plus 1 over x minus 2. And we know that x cannot equal 2 because this would make our denominator 0. So this would be our inverse right here. Now, in order to actually check it, we can plug them back in. I think this is kind of difficult when you have fractions. It's a little easier to mess up than the original problem. So what my suggestion actually would be to find the inverse of your new function and make sure that it maps back to the original to make sure that it works. Okay, now let's solve some exponential equations. So let's say we have 2 to the power 3x minus 1 equals 32. So what we want to try to do is write these so that they have the actual same base, okay? And once we have the same bases, we can ignore the bases. So 32 is really just 2 to the 5th power. So we can write this as 2 to the 3x minus 1 power equals 2 to the 5th power. And now since we have the same bases, we can just ignore our bases. So we just say 3x minus 1 equals 5. And then we add 1 to both sides and divide by 3. So we get x equals 2. And then if we plug this back in, if we plug the 2 into the original, we have 3 times 2, which is 6 minus 1 gives you 5. And then we know 2 to the 5th is equal to 32. So this one works just fine. And then this one over here, it looks a little nasty, but we're just going to try to clean it up, and then hopefully we'll have everything with e to some power, and then we can ignore the bases. So what's done here is we've taken the left-hand side, we've left it alone, and then we've rewritten this as one fraction. So we have e to the negative 4x, because when you have a power to a power, you multiply. So that's this right here, divided by e to the 3x. And whenever you have division and you have the same bases, you can actually just subtract these two things. So we have negative 4x minus 3x, and that'll give you negative 7x. So we have e to the 2x minus 1 equals e to the negative 7x power. And then since we have e's, we just ignore the bases, and we're left with 2x minus 1 equals negative 7x. And we just subtract 2x from both sides, divide by negative 9, and we get x equals 1/9. This one is not so easy to check because the numbers are really nasty, but if you plug it in, it will work. All right, let's look at a logarithmic equation. So let's say we have log base 3 of 4 equals 2 times log base 3 of x. Now for this one, since you have this 2 here, you can actually take it and make it an exponent. Okay, so exponents can be brought out as factors, and factors can be brought up as exponents. So now we have log base 3 of 4 equals log base 3 of x squared. That's from this rule right here. And since we have log base 3 and log base 3, since they're the same, we can actually ignore the logs, and we're just left with 4 equals x squared. And then we would take square root of both sides, and we'd get x equals 2 or x equals negative 2. Now, one important reminder is that the domain of logarithmic functions is going to be positive numbers only, so we always need to check for extraneous solutions. So if we take negative 2 and we plug it in here, if you try doing log of negative 2 in your calculator, it's going to come up with the domain error. So this one is extraneous, so x equals 2 is the only valid solution here. All right, let's look at this example here. We have log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. Now, since we have addition here, we can actually change this to multiplication. And we also have the same base, which has to be true. So we have log base 2 of x plus 2 times 1 minus x equals 1. And then we rewrite this as exponential. So this 2 is our base, and we have 2 to the 1st power equals x plus 2 times 1 minus x. That's just this function right here where we can change from logarithmic into exponential. And then we go ahead and factor this out. So we have 2 equals negative x squared minus x plus 2. And then we subtract 2 from both sides. So we have x squared plus x equals 0. And we factor. And we get two solutions, x equals 0, x equals negative 1. And you need to make sure that both work. So if we plug 0 in, we have 0 plus 2, which is 2. There's no issues with having log of 2. and we also have 1 minus 0, which is 1, which is also fine. And if we take negative 1 and plug it in, negative 1 plus 2 is going to be positive 1, so that one's okay. And 1 minus negative 1 is just going to be 2, so this one works as well. So both solutions are actually in the domain. The solution is negative, but when we plug it in, we have a positive value for our logarithm, so there's no issues there. Now let's take a look at this example here. We have 3 to the x equals 7. Anytime you have an x in your exponent, in order to get rid of it, you need to take log or natural log. So we're going to take log of both sides, natural log of both sides. So we have ln of 3 to the x power equals ln of 7. And then we take our exponent and we move it out front. So we have x times ln of 3 equals ln of 7. And then we just divide. So we get x equals ln of 7 over ln of 3. This would be our exact answer, and then you put it in your calculator to get 1.771 as an approximate answer. And you can check this very easily by plugging in 3 to the 1.771 power, and you're going to get something really close to 7. It's not going to be exact because you rounded this answer, but it should be pretty close. Let's take a look at this one here. Let's say we want to solve the equation 5 times 2 to the x power equals 7. So since we have an x in our exponent, we're going to want to use log or natural log. But in order to do that, we want to get this piece by itself first. So we actually want to divide by 5 first. So we have 2 to the x equals 3/5, and then we want to use log or natural log. So we've used natural log here. So we have ln of 2 to the x equals ln of 3/5. And then we move our exponent out front. So we have x times ln of 2 equals ln of 3/5. And then we divide by ln of 2. So we have x equals ln of 3/5 divided by ln of 2, which gives us negative 0.737. And again, you could take this and plug it into the original, and you should get an answer very close to 3 when you do that. All right, let's take a look at this one right here. This is a little bit nastier because we have different bases here, so there's no way to rewrite them the same way, and then they both have exponents in them. So in order to get rid of them, you have to take log or natural log. So we have ln of 2 to the x minus 1 power equals ln of 5 to the 2x plus 3 power. Now you can always take your exponents and stick them out front, so that's what we're going to do next, but you have to put parentheses around them. So we have x minus 1 times ln of 2 equals 2x plus 3 times ln of 5. And then we went ahead and distributed. So we have x times ln of 2 minus ln of 2 equals 2x ln of 5 plus 3 ln of 5. And then we get everything that's attached to an x on one side and everything else on the other. So for example, this 2x ln of 5, we're going to want to move that over here. And this negative ln of 2, we're going to want to move that over here. So we have x ln 2 minus 2x ln 5 equals 3 ln 5 plus ln of 2. And now that we have everything with an x on one side, we're going to factor out an x. So we have x times ln of 2 minus 2 ln 5 equals 3 ln 5 plus ln 2. And then we divide both sides by what's in parentheses here. So our exact answer would be x equals 3 times ln of 5 plus ln of 2 divided by ln of 2 minus 2 ln of 5, which gives us negative 2.186 as our actual x value. And you could plug this back into the original to make sure that it works. You'd have to plug it into the left-hand side and the right-hand side and make sure that your answers are approximately equivalent.